So, last time we looked at a very special case of Hensel's lemma. We proved that 2 has a square root in Q7, and we did this by some limiting process. So, what you do is you start with a solution modulo 7, lift it to a solution modulo 7 squared, and lift that to a solution modulo 7 cubed, etc., and in the limit we get a solution in Z7 or Q7. We are going to look at a generalization of this, and rather than just solving for roots, which is same as finding a polynomial of degree 1 that divides your given polynomial, we are going to prove a result about factorizing a polynomial if you know factorization modulo the maximal ideal. Okay, so we are going to prove a lemma. This is called Hensel's lemma. So, let me write that name, Hensel's lemma, and the version that I am going to state it is as follows. So, let f of x be a polynomial in O sub p of x, right, the ring of integers in the completion of k at p. We denote f bar p of x by its image in k p x by as reduction modulo p of f of x. Okay. So, there is a natural map from OPX to KP of x, and under this map f of x goes to f bar of x, right, that is my notation. Now, if this reduced polynomial, this polynomial mod p factorizes as product of two polynomials where phi 1 and phi 2 are co-prime. So, you can define what two polynomials being co-prime means in Kp of x. Okay. Then the polynomial f itself factorizes in OPX, then f of x is f1 of x times f2 of x in OPX such that, well, first of all, you see the degree of f bar could be strictly less than degree of f. So, I can't say that degree of phi 1 should be degree of phi f1 and degree of phi 2 should be equal to degree of f2, but I can ask that for one of those polynomials, right. So, such that degree of f1 is equal to degree of phi 1 and fi bar of x, this is equal to phi I of x for I equal to 1 and 2. So, that is the statement of Hensel's lemma that we are going to prove, and this lemma, so if you apply this with phi of 1 equal to x minus the root mod p, then you get a root in OP of the polynomial f x. So, so that is how you apply this to find a root. Okay. So, what are we going to do? Well, to begin with, again as I said, you just lift, you have a factorization modulo p. So, you try to get a factorization modulo p square and p cubed and so on, and then you take the limit, right, that is what we are trying to do. Okay. So, so we construct f1 of n and f2 of n, this is f1 n x f2 n x for n equal to 1, 2 and so on, such that the following happens, such that, well, first of all, f1 n bar, this is equal to phi 1 of x, f2 n x bar, this has yeah, okay, I do not really want to say anything about that, but I want to say that degree of f2 n of x is less than equal to degree of f minus degree of phi 1. Okay. Furthermore, I want to say that f n gives me, f I n gives me factorization modulo p to the n. So, I want to say that p to the n divides f of x modulo f 1 n x f 2 n x, and p to the n also divides f I n plus 1 x modulo maybe, yeah, maybe let me say it in the following way, sort of rather, yeah, let me say that p to the n minus 1 divides f I n minus, so this is x minus f I n minus 1 x for all n, yeah, okay. It does not matter, right? Let me not write that. So, we want to construct things like that, and so what do? We construct this inductively, we construct such f I, so this should be I equal to 1 and 2, f I n x recursively right. So, what is f I 1 of x? These are simply any lift of phi I of x in OP of x, right. Remember, the map from OP of x to KP of x is surjective. So, I can always lift any element in Kp of x to an element in OP of x, and since I am only interested in sort of divisibility mod p, I do not care about what lift I take, right. So, now let us say we have constructed f I 1, f I 2 and so on up to f I n, then we want to construct f I n plus 1 of x, right. So, having constructed everything up to n, we want to construct the n plus 1th object, and so what we do is we just you take pi to be in p, but not in p squared, and then you write f I of n plus 1 of x to be f I of n right, plus pi to the n times some g I n of x, right. So, that is what we, so we want to find g I n of x such that p to the n plus 1 divides f of x minus f1 n plus 1 x f2 n plus 1 x. By the way, when I say that this prime ideal divides this polynomial, it means that it divides each of the coefficient of this polynomial. Okay. All right. So, what do? I take f1 n plus 1 x times f2 n plus 1 x. I just consider this f of x minus this. So, this is f of x minus f1 n x plus pi to the n g1 n x f2 n x plus pi to the n g2 n x. So, I can rewrite this as f of x minus f1 n x f2 n x minus pi to the n, and then I can I gather the terms with pi to the n's in them. So, this will be f1 n x g2 n x plus f2 n x g1 n x minus pi to the 2n times g1 n x g2 n x. So, as before, as in the special case, this last term is irrelevant if we want to look at things mod. So, this is already 0 modulo pi to the or p to the n plus 1. So, that term is irrelevant, right. So, I just wrote it in the wrong order. This should be congruent to 0 mod p to the n plus 1. Okay. All right. So, we want g1 n x g2 n x such that f1 n x g2 n x plus f2 n x g1 n x is congruent to 0 modulo p, because there is already a pi to the n in here, right. But what is f1 and f2 modulo p? This is just phi 1 of x g2 n x plus phi 2 of x g1 n x is congruent to 0 mod p. Right. Okay, and I think I have made slight error somewhere. I'm trying to figure that out. No, sorry, I don't want this to be sorry, this shouldn't be 0 mod n. What I want this is sorry. I want this to be f of x minus f1 n x f2 n x divided by pi to the n mod p, and so let me call this h of x mod p. So, I will write what h of x is on the next page. So, h of x is f of x minus f1 n x f2 n x by pi to the n. Okay. All right. So, let us recall what we want to do. We want to find g1 n x g2 n x such that phi 1 x g 2 n x plus phi 2 x g 1 n x is congruent to h of x mod p. But as phi 1 and phi 2 are co-prime, we can always find a solution to this. Right. Remember what these polynomials being co-prime in this means, it means that the ideal generated by phi 1 of x and phi 2 of x is the whole ring. Right. That is what being co-prime means, and so we can always find a solution. All right. So, once we have found a solution like this, it is easy to prove that it satisfies all the properties that we want, right. Okay. I mean, the only thing to verify is that degree of f1 n plus 1 is same as degree of phi 1. But for that we could always take, so take g1 n x degree of this to be strictly less than degree of phi 1, right. All right. So, as long as we do this, if we lift, we can take a lift such that this happens, and then we are fine. Okay. So, the remaining part I will leave as an exercise for you to figure out. So, let me write down a corollary of this. So, let f of x be in OP of x if there exists alpha in Kp such that f bar of alpha is 0, this is in Kp, and f dash, so this is derivative of f, this is not 0, then there exists alpha tilde in OP such that f of alpha tilde is 0, and there exists a unique alpha tilde like this, and alpha tilde is congruent to alpha mod p. So, you should take the proof of this as an exercise. This is a simple application of the lemma that we just proved, Hensel's lemma. Okay. So, this is exactly what we proved last time in the special case when p was 7 and f of x was x squared minus 2. So, as a corollary we get the following. So, now let L over K be a finite extension of number fields okay. P and P be primes of L and K respectively, such that capital P divides a small p o L. Okay. If alpha belongs to O capital P, then alpha is integral over O sub small p. So, this is kind of what you would expect, and this turns out to be true. In particular, trace from K capital P to, sorry, not K, L capital P, LP to KP of alpha, and norm from LP to KP of alpha, they are both in O sub p. Okay. And this kind of the way we construct LP and KP and OP etc., they it uses some analysis, whereas this is a purely algebraic thing. So it shouldn't be kind of surprising that the proof of this corollary is somewhat involved. Okay, it's not one line. Okay, so what I am going to do is let E be the largest power of P dividing POL, right. So, P to the E is the largest power dividing POL, that is what this means. Okay. Now, O mod, yeah, let me write it like this. Kp is a finite dimensional K sub p vector space, right. So, what I can do is I can let alpha 1 up to alpha n be so okay. So, I want this to be a subset of O capital P such that alpha 1 bar up to alpha n bar is a basis, is a K sub P basis of K sub capital P, right. I can always do that. I can take any basis of K sub capital P and I can lift it to elements of OP, and that is how I get these elements. So, then pi to the power I alpha j, if I take this set where I ranges between 0 and e minus 1 and j ranges from 1 to n, forms a set of generators of OP as an O sub P module. Because what I can do, so maybe you can take this as an exercise, but let me say orally how this is done. If I take any element of O sub capital P, I can look at it mod small p to the power E, and then it is clear that I can write it as a linear combination this way, right, and therefore I can get a up to an element of OP I can get it, I get that this is a set of generators, right. So, that is roughly the idea, and hence we get therefore O sub p is a finitely generated O sub small p module, hence every element of O sub p is integral over O sub small p, right. Okay. So, that is what we wanted to show. The next one, so let me so if you look at this corollary that we had before about finding roots, then there is this condition that that f f prime, the derivative of f at evaluated at alpha is not equal to 0, right, and sometimes we may not have this condition may not be fulfilled, right. So, we want a statement where we do not use this. So, here is kind of a somewhat more general version of Hensel's lemma. So, let f of x in OP of x be a monic polynomial. So, we did not have this condition in before. Let alpha be in OP such that mod of the valuation of alpha f of alpha is strictly less than valuation of f prime of alpha squared. Then there exists a unique alpha star in OP such that f of alpha equals 0 or alpha star equals 0 first of all, and alpha star minus alpha, the valuation of this is less than or equal to valuation of f of alpha divided by valuation of f prime of alpha, and this thing in turn is strictly less than valuation of f of alpha. Okay. And so, again the idea would be to construct sequence of elements getting better and giving better and better approximation. Okay. So, proof construct alpha 1 which is just alpha. So, you start with alpha, alpha 2 etc. In OP such that the following holds: f of alpha n plus 1 is less than equal to valuation of f of alpha divided by valuation of f prime of alpha squared. I hope I had squared there. Okay, no, sorry, there is no squared in the, but this is less than no, sorry, what am I doing, times valuation of f of alpha n, and this is strictly less than valuation of f of alpha n. Moreover, so that is one condition, and then f prime of alpha n plus 1 is equal to valuation of f of alpha, and what happens to their differences. So, we want this to be a Cauchy sequence, right, otherwise how would we take limit? Okay. All right. So, we want this thing, right, and because of the way things are set up, right. So, f of yeah, okay. So, valuation of alpha n plus 1 minus valuation of alpha n, this goes to 0 as n goes to infinity. Maybe you can take this as an exercise to deduce it from other things. So, how do I do that? Well, I just take alpha n plus 1 to be alpha n plus beta n for some beta n, and I evaluate this at alpha n. So, I get this, and this I can write as f of alpha n plus f prime of alpha n beta n plus higher, so plus multiple of beta n squared. This is Taylor series expansion, right, and this is only for polynomials. So, this is kind of easy, you know, it's so you can take beta n to be minus f of alpha n divided by f of f prime of alpha n, right, and this would ensure that the first two terms cancel and you get so if you take beta n to be this, then the first two terms cancel and f of alpha n plus 1 is simply a integral multiple of beta n squared. Okay. All right. So, so the only thing to, yeah, maybe I'll leave this as an exercise for now, is prove uniqueness of alpha star. Okay. Yeah. So, what we did today was look at various versions of Hensel's lemma, including this last one, which is which only applies to monic polynomials, but otherwise it is kind of general in some sense. So, if you restrict the original Hensel's lemma to monic polynomials, this is a more general version for it. And next time we will apply this Hensel's lemma to prove results about local fields. Thank you.